Okay, so we're now connected in Space Analyzer. We're using the latest release and we're looking at the ribbon bar view. So for you guys it looks slightly different, but it's kind of the more updated, kind of fresh look for Space Analyzer. So yeah, we've got a laser tracker in, we're connected, we've got some CAD, and we can see the laser tracker doesn't know where it is relative to the CAD model as of yet. So we're going to align to the CAD using the reflector we can see there in the video view and the accessory underneath, and we've got some points on the model in a similar place. We've got P1, P2. So the idea is we locate the instrument via a right click, and there's an option to measure nominal points. So we're going to do a best fit alignment by measuring the nominal points, similar measured points in the same location, and then overlay them. That's the principle. So the nominals we're going to measure are these, and then we get the window up. Just move that out of the way so we can see what's going on. We're going to go into a group called Locate Instrument Measure 1. Maybe we call this just measured. Apply. Okay, so we're in number 1 there, so we can measure. To trigger the measurement there. Okay, if we scroll back on the mouse, you can see the laser tracker has no idea where it is as of yet.
Just as a visual aid, whilst we're actually using the laser tracker in 3D mode to measure 3D points, we're using the 1.5" reflector which comes with the tracker, and we're using what we call a pin nest, which is something you're probably familiar with, but it's a nest with 3 land items that the reflector snaps into so that it's always in the same orientation, and then there's a shank on the bottom which fits rather nicely into each of the holes. So these are sized and made to suit whichever feature that you're measuring. So when the reflector's in the nest, the centre of the reflector is 25mm above the base of the reflector, and in the software you can see that each of those nominal points are actually 25mm off the surface as well. So this is a very traditional method of booking in or aligning the tracker to a part, something you're probably familiar with, but we thought we would cover anyway. So when I turn the reflector around and face the tracker will lock on, and you'll see a green light on the tracker itself over here in the image. So that means we're locked on and ready to go. So I'm now just going to place the pin of the pin nest into hole number 2, drop it down, and we can trigger the second point.
Okay, go to number 3. So we're using a 960, but what we're seeing now on the screen is what you'd be, it'd be exactly the same if it was a 930.
Yeah, so the difference really between a 930 and a 960 are the numbers in the middle, so the 3 and the 6. The 3 in the 930 signifies 3D measurement being an XYZ coordinate from the centre of the reflector. The 6D tracker, where we can use the T-probe and the T-scan, that relates or refers to the 6DOF technology in the actual T-probe and T-scan that allows us to hold those items at any orientation and still take measurements. And we'll explain a bit more about that when we use those instruments.
Okay.
Moving to number 5.
Okay, so we've measured everything and we're seeing an XYZ deviation per point and also a magnitude. So they're the results of the alignment. So we've got 7, 8, 4, 13 and 4 microns. So we can do finish locate instrument. And obviously if we zoom out now, we can see we're aligned. So once we got to the 3rd point, you may have noticed that the instrument kind of located to the part. So that's kind of why after 3, it's kind of trying to fit the data as we're going along. Okay, just in regards to a watch window, let's just right click on the CAD and get some real feedback. So we've got the watch window. We'll just switch to the reflector only mode. Whenever John puts the ball on the surface, you can see we're aligned to within a few microns based on the alignment, the residuals of the best fit alignment.
So yeah, just a small number of microns wherever I put this reflector on the surface of the CAD, and it's extracting the nominal position from the CAD data and giving us a deviation. So yeah, it's safe to say we're very well aligned. The system and the software is taking into account the offset between the surface of the CAD and the centre of the reflector. The centre of the reflector is always where we actually get the measurement result. Just something that you may have noticed, here's a half-inch reflector in comparison to an 1.5-inch reflector. So these are available if your parts are very tight and you can't get in there, you can use a half-inch reflector. We actually do a 7/8-inch reflector, which is kind of somewhere in between the two. But 1.5 inches, they're really nice and handy to use and easy to hold, so we'll continue off with this one. But there's all sorts of different reflectors you can use.
Okay, up front I've created a couple of features we're going to measure. So we're going to measure this 80mm hole in the centre. And we haven't got a T-probe because we're using the 930. That's kind of what we're showing here. But we can use a pin nest. So we'll flip back to the pin nest and we can measure this hole. So I'm going to start the kind of inspection off. We can see it's highlighted on the CAD. And you know, if I had a remote control, if John had a remote control, he could trigger it himself or using stable points. Okay, so we've got the first measurement. It's counting up. You can see on the corner of the graphics there, we got number 1. We'll press measure again.
I actually moved the nest then whilst we were taking the point. It rocked a little bit, so can we check to see what the RMS was there, or is it worth deleting that point?
Yeah, so we can open the point group up, we can double click the point. If we go to measurement details, there's information. So we've got a full traceability chain of the measurement, and we've got the RMS error of 0.167, so it's a bit high.
Yeah, it moved just a slight bit whilst I was taking the point, so
that's a good point. So it's good to see you've got full traceability with Spatial Analyzer. So we're going to delete P2, and we can also set a threshold for that to reject as well.
Okay, that's better. Next one. What am I going to do?
We'll do 6. We're going to do 6 measurements to make the circle. 3 is the bare minimum. Having some redundancy is good. We get some RMS, like a quality factor of the circle. Okay, we'll stop that. We can stop trapping that now. Okay. So I right-clicked on the relationship then, or the feature we've just measured, and we can get graphical feedback straight away. So we've got a nominal, measured, and a deviation of 17 microns, and we've got the position. So by aligning to the CAD, measuring with a pin nest, we've kind of established the size and the position of the hole.
So that's the same for any type of standard geometry, so it could be a hole or a slot or an ellipse or a cylinder. So any kind of prismatic geometry you can measure with the reflector itself or with the aid of a pin nest or some tooling.
Okay, so we'll jump on to the next feature, and it's this front profile, and we're going to use the reflector to scan the surface. So we'll just switch to reflector. And so we're going to use spatial scan mode, which is the kind of the icon where you can see the kind of dots that join together. So we'll click that. Okay, it's asking us to move the reflector to the surface, which John is doing. And now if he runs it on the surface, we can see we're taking measurements, and we've got it set up so as we're measuring, we're getting some blotches appear on the screen. Okay, and we get the spread of the dispersion in the colour bar on the right hand side.
So with the AT930 and the AT960 delivering data at 1000 Hertz, if I wanted to, I could go a lot quicker, but I'm just ensuring that I'm holding the reflector on the surface of the profile we want to measure. It will take shots or hits in fresh air if I was to actually move the reflector off the surface, so got to be quite careful you keep the reflector in contact, but the tracker is capable of capturing that data way quicker than I'm capable of moving my arm, really.
Yeah. So we can see the deviations there. So we've got 9 microns positive, and then we've got -40 in a negative, which means there's too much material off that face. We can make these vectors longer, so we'll just make them a bit longer so we can get an understanding. Close that off. So maybe we'll do top view, drag a box round so we can see, show the call out as well. Oh. So we've got a nice view, we've got the deviations on the surface face, and we can make a quick report out of that if required. So if we right click on relationships, we can make a PDF of just what we've measured. So put that on the desktop. Okay, so there's our screen grab, and then we get some information on the hole and also the surface profile. So we did 136 measurements, and we've got they were all within the plus or minus 0.1 that we kind of specified. We'll just close the report off. Yeah, so that's kind of what we wanted to show you with the AT930.
I think there's one more really important feature that is standard on all of the Leica trackers that we offer at the moment, called Power Lock. It's a function that was introduced one previous generation ago, but I don't think those systems exist at BAE, so you might not have seen this. So Power Lock is basically a function whereby when the laser tracker over in the corner of the screen there is locked onto the reflector with the laser beam. I'm not sure if you'll be able to see this, but if I put my hand in front of the reflector, you'll see on the software the indication goes red in the top left corner to show that we're no longer locked onto the reflector, and you can see a red and a blue light flashing on the actual tracker head itself. So at the moment the tracker is searching for the reflector, and what I can actually do is move the reflector, but if I take my hand away, the tracker immediately sees where the reflector is, moves slightly and locks back on, and we go green almost immediately. So you can do this in mid-air, you can even be moving it, so you can block the beam as many times as you like, move everything around. As soon as the tracker can see the reflector, it locks back on and goes green. This is an absolute godsend on the shop floor. You've got people driving past with forklifts, cranes going past. If you have to climb up some access steps to get to the top of the jig, for example, you just introduce the reflector into the scene when you get to where you need to do your measurements, and the tracker will immediately lock on. So again, really great for health and safety, really good for productivity. In the older days, if you broke the beam, not only did you have to kind of find it yourself and then move the reflector to the beam, it sometimes took a few moments for everything to lock back on. So Power Lock is absolutely incredible, and you know, the younger generation kind of can't live without it because it's all they've ever had, and the older generation of operators can't believe what they're seeing when they actually see it. It's a serious improvement, so it's really good for productivity.